Hello, everyone. Welcome back to Banach Spaces webinar. Today we have Gideon Schechtman from Weizmann Institute of Science, and he is speaking on number of closed ideals in the Banach algebra of operators on capital LP. Gideon, go ahead, please.
Thank you. So the main new thing I'm going to speak about is a joint paper with B, but I'm going to give some kind of a general introduction, and it will include
Are you far from microphone, Gideon? Maybe you can get close to
no,
microphone.
I don't.
Okay, all right.
Is it okay? And so I mentioned also a not very old result of some 2 years old result of Bill and Gilles PCM. So let me start with kind of a general introduction. I'm going to speak about L of X will denote the Banach algebra of bounded linear operators on Banach space X. And I'll speak about ideals in this space. I always speak about two-sided ideals. So an ideal I is a linear subspace of L of X, which is closed by multiplication by a general operator from L of X, both on the right and on the left. There are some in any Banach space there are some classical closed ideal. One is I'm talking only. I will be interested in closed ideals. So the set of all compact operators, the finite dimensional, finite rank operators are always in any ideal. This is very easy to see. And so the set of compact operator, if X has approximation properties, the closure is a set of compact operators, and this is always the smallest idea. Another one that may occur or not is a set of weakly compact operators. Sometimes it coincides with the whole space if the space is reflexive. This is only if actually the space is reflexive, but sometimes, but if not, then there's a different ideal. Another one is a space which will be particularly important for us, is a space of strictly singular operators, operators which are not isomorphism and restricted to any infinite dimensional closed subspace. Okay, so this S of X will play some role in a minute. There is another one which is interesting, or it's not always one, sometimes it's more than one, and this is a maximal idea. So you can always, whenever you have an ideal, even an algebraic ideal, so not necessarily closed, it is containing some maximal idea, maximal with respect to inclusion, I mean, and this maximal ideal is always closed already. This is easy to see because if it is I'm talking about proper ideals, okay, one which is not all of L of X. So if the identity is not there, also some neighborhood of the identity is not there, it cannot contain an invertible operator. So there is an open set which is not in this thing. So the maximal ideal is a proper ideal, and it is closed. Now, sometimes there is more than one maximal ideal. It's the question of finding out what are the maximal ideal is sometimes very hard. I'm speaking, of course, only about classical spaces or LP spaces, and there it is known what they are. The maximal idea there is, well, maybe first of all in general, I'll denote by M of X the set of all operators on a Banach space X such as the identity does not factor through X. So all operator T such as the identity is not of the form BT A, and it is quite obvious that one has to think about it for a minute, but it is quite easy to see that M of X, if it is ideal, if it is if it is a subspace, if it is closed under addition, this is the main thing, then it is a maximal ideal. Now, not always it's closed under addition, but in the classical cases, in the LP cases, which is what interests me, it is, and also it is known that this is the same, this maximal ideal is the same as the LP strictly singular operators, namely all operators which are not isomorphism when restricted to any subspace isomorphic to capital LP. Capital LP for me is capital LP of 0, 1. Okay. So this is written here, we say. So this is known, but it's not trivial. For people one, it was proved by Aflo and Starbeard, and for the reflexive range, it was proved by Johnson, Moran, Safri, and Mishra. So there is this maximal ideal in LP. There is this maximal ideal, which is the same as the same as the LP strictly singular operator. This is and it is unique. There is a unique one. Yeah. And so there is I'm going to give kind of examples of ideals. So all ideals, there is a common way of constructing. Let's first start with a not necessarily closed ideal in L of X. And this is, when you do it, you take some operator, not necessarily on X, or between some two Banach spaces, and I denote by I call it U, and I of U is a collection of all operators that on X, which factors through U. So all T in L of X, such as there are A and B in the respective spaces, such as these A, U, B, really. Okay. Now, this is not necessarily an idea, such a thing, because again, the problem is, it's very easy to see that it satisfies these conditions that multiplication on the right and left reserve it, but the problem is that it may not be a subspace. However, it's easy to in many situations it's easy to see that it is subspace, and one way to ensure it is to if U is such that if you look at U plus U as an operator from Y plus Y into Z plus Z, if this factor through U, then you get an ideal. Then it is closed under addition. It's quite easy to see. So, and this is only kind of U that I'll use. Okay, so this is one way to build the ideals. Another way which I'll use is the following. So you have now a set of operators on L of X. Okay, and you look at all finite sums of such things, finite sums of such combinations of AI T of alpha I bi, where alpha I are from this set, just finite sums. AI and bi are general operator on L of X. You look at all such things, you allow repetition, and then it's easy to see that this is an algebraic ideal. So its closure is something that I'll be interested in. Okay, these are the two. So these are the two kind of constructions that I'll be using to build in this lecture. Okay, there is a notion of large and small ideals, which is not very important here, but I'm bringing it mainly because I want to ask some questions, and for that I want some open problems, and for that I need this notion. So again, I remind you that I of U is a set of all operators on L of X which factors for U, and S of X are the strictly singular operators. I call an ideal small if it is contained in the strictly singular operators, and otherwise I'd call it large. Okay, so it's just names. Let me give you examples. So an example of a small operator is if U itself is strictly singular, and u plus u factor for u, so that I'll get really an ideal, then the closure of I of u is small. This is quite clear. And an example of a large ideal generated like that is if you take a complemented subspace y of x, and you look at u to be the restriction, the identity of y, or if you want the projection onto y, it is the same. But you need some, so then if you have it like that, then I of u would satisfy again this ideal property, but to make it also a subspace, you need something more. For instance, if y plus y is isomorphic to y, then you get this. So projection on all operators which factor through a projection onto a subspace which is isomorphic to its square for a large ideal. It's quite clear, yeah, that this is not strictly, u is not strictly singular. I'm talking about infinite dimensional subspace. And this is just a notation. Instead of writing I of y in such a case, I'll write just I of y. Okay. So now I'm coming to the LP case. Up to now it was general spaces. Now I'm coming to the LP spaces, and I'll start with L1. So I remind you that the ideal is small if it is contained in a strictly singular operator. Otherwise, I call it large. So here are some examples, some kind of classical examples of small closed ideals. So the compact operators, the strictly singular operators on L1, the weakly operators on L1, but it's known that the weakly operators on L1 are the same as the strictly singular operators on L1. This is a Danforth Petit property of L1. So these are some small ones. Some large ones in L1 are the operators which factor through little L1. Yeah, this is like a complemented subspace of little L1. The largest ideal, remember, these are the operators which are L1 strictly singular. Do not preserve isomorphically a copy of capital L1. And there is another one, the Danforth Petit operator. I will not speak about it too much. There is some nice property of largeness and smallness in L1, which unfortunately is not shared by other spaces. And this is that there is some kind of a border ideal. This is the operator which factors through little L1. So every large ideal contains this operator which factors through little L1, and this operator which factors through little 1 are contained in contains any small ideal. I'm sorry, I didn't say it correctly. Any large ideal contains this special ideal, and this special ideal contains every small ideal. Okay, it turns out that this is the case. So this notion of small and large makes a lot of sense in L1, not so much in other spaces, maybe. Now, in L1, until recently, until some 3 years ago, this was all that was known. So, and these are all the ideals that were known in L of L1, only 6, I think, or something like that. And Pitch asked in his book whether there are infinitely many. So, this is something we solved with Bill, Gilles, and I. Okay, I'm sorry. I have a slide here about explaining what is the difficulty in building ideals in L1 or in general, but I'll skip it because I don't think I left enough time. By the way, how much time do I have? 50 minutes or an hour?
Yes, we can do as long as you want. We can do 50 minutes, yes.
couldn't hear you.
Yeah, we usually do 50 minutes and then
50 minutes.
discussion after that.
It's fine, it's fine.
But we can go a couple more minutes more, yeah. Okay.
Sure. Definitely. Okay, so I skipped this difficulty slide. And so Gilles, Bill, and I proved some years ago that there are at least two to the continuum of closed ideal in L1 that turn out to be all small. Okay, and there is some duality, non-trivial duality, which gives it also in L infinity. By the way, in L infinity, in L infinity, all ideals are small. There is no, well, this is quite easy. I mean, let me, but this is not the case in the other AP space. So I want to ask some questions related to that. This is why I also give the notion of smallness and largeness. So it's open. First of all, it's open whether there are infinitely many large ideals in L of L1. Closed, of course, I'm always talking about closed. And this is connected with, of course, with the unsolved problem of whether there are infinitely many complemented subspace, non-isomorphic complemented subspace L1. Actually, we don't know if there are more than two. So the question is whether every infinite dimensional complemented subspace of L1 is isomorphic to either little L1 or capital L1, which of course is more interesting than anything I'm talking about today. Also open is whether there are more than 2 to the Aleph 0 closed ideal in L1. The maximal number, this is simple cardinality reasoning, is there can be at most 2 to the continuum closed ideal, but there is of course a big gap between the continuum and the 2 to the continuum. We don't know that. Let me just, I will not speak at all about this theorem with Gilles and Bill, but let me just say something about the proof. Where do we find these closed ideals? So the ideals that we build are a family indexed by Q between 2 and infinity. They are all of the kind operators which factor through some operator which we call U of Q. And this U of Q is an operator going from little L1 to capital L1. It's of the Cantor group. It's better to think about it that way, which maps they map the unit vector basis in little L1 to a carefully chosen lambda Q set. Okay, lambda Q set is a set of characters such that the L1 norm is equivalent to the Q norm. This is a classical thing in harmonic analysis. And the point is that you need to find you have to use some dense set of such, more or less a densest set of such characters and some more properties of this. I'm not entering into that. The solution uses a construction of, can use a construction of Bourgain, a solution to the lambda Q problem of ruling. But actually one can also do it in a simpler way. It's nice to use this kind of problem. It's very easy to define these ideals. It's quite easy to define. The problem is, and this is usually the problem, is to show that all these ideals are different. Okay, this is really the thing. Okay, this is all I want to say about the L1 case. And now I come to the main thing, the main topic, which is the LP case in the reflexive range. And let me start with large ideals, or let me start with what was known. So there are, of course, some classical ones, some classical ideas, but it's known that there are infinitely many isomorphically different complemented subspaces of LP. This was first proved by myself in 1975. And also each of them is isomorphic to its square. This just comes out of the construction. So by what I said before, there are infinitely many closed ideal in LP, and they are all large. Okay, and a little bit later, together with Bourgain and Rosenthal, we proved that there are actually Aleph1 isomorphically different complemented subspaces of LP. Again, each isomorphic to its square. So there are, so it immediately follows that there are Aleph1 large closed ideal in LP. But this left open the problem of when there are several problems that were left open at that time. So of course, at that time I didn't think about the ideal, or I don't think that Bourgain wasn't that thought about ideals, but Pitch thought about ideals, and he noticed that this results give you infinitely many ideals, or Aleph1. Well, Aleph1 actually came after the book. So. But this left open the question whether there are more than Aleph1, large or small closed ideals in LP. And maybe even there are, they say there is an upper bound of 2 to the continuum. Maybe there are even 2 to the continuum, large or small closed ideals. Okay, so this is another question of Pitch. So this was open for a long time, but quite recently it was attacked by Thomas and Andras, and they proved the following. So this was some 2 years, well, actually 2 years ago, or probably 4 years ago. And it solves the first problem for small ideals. There are a continuum of small ideals in L of LP, so in the whole range. The construction, I'll say something about the construction, very little. So the way they build all the ideals are of the form, a set of operators which factor from some U, and all these U's are basis to basis maps from little r to little s, but the bases for little r and little s are not the standard bases. They use XP space of Rosenthal, which I also use later. So we'll get back to it in a minute. So this was the situation until 2 years ago, and I think that now I come to the theorem. Yeah. So very recently, some half a year ago, a little bit more, no, almost a year ago, we proved, Bill and I proved that there are actually 2 to the continuum closed ideal in L of LP in the reflexive range. So I remind you, we don't know this in L1. It's only the reflexive range. And we actually, the construction, the natural construction gives you that number of large closed ideals, but it's easy to adjust it to get also the same number of small closed ideals. Okay, so in this case, okay, we know, and this is a number. I mean, you cannot get more than that. As far as the number is concerned, this solves the problem. Of course, you can ask many questions about the structure of ideals, and there are many, many other questions. But as for the number, this completely solves the problem. Okay, so the proof. The proof relies on properties of the space spaced by independent random variables in LP, which is the topic mostly which was investigated mostly by Rosenthal in the beginning of the 70s. And this is again the space XP, which also Andras and Thomas use. But we use it in a completely different way. So I want to describe the describe a little bit the proof. Of course, not the details, it's quite technical. It's not long, the paper is quite short, but it's not so easy. quite involved technically. Okay, so let me first, any questions until now? No, okay. There is I don't monitor the comments, so, okay. If there are any questions in the, whatever in the comments.
Yes, so far there are, yeah, go ahead.
Sorry,
Okay.
may I ask a question?
Sure.
Oh, sorry. I wanted to make it large screen. Your result, Professor Schechtman, your result that there are 2 to power 2 to LF0 number of both small and large ideals. Is it, can it be paraphrased like this, that there are 2 to LF1 number of ideals, the different closed ideals in the Banach algebra LLP 01 for p greater than 1, not equal to 2 and less than infinity. In other words, is here assumed that the axiom of choice holds together with continuum hypothesis?
No,
because
no, there are no set theoretical assumptions. This is independent of the
okay,
axiom.
thank you very much. Yeah.
This was part of the problem. We knew before that there are Aleph1, even to get the continuum. I mean, okay. So
Yeah,
anyhow, it does not rely on any set theoretical assumption.
You also mentioned that direct sum y and y may be equal to y. What is condition to y that such equation holds?
Y plus y is equal to y?
Yes, direct
Not
sum.
equal, isomorphic to y. This happens in many cases in all classical spaces. And there is no, I don't think that there are spaces in which it does not hold, but it in all the classical cases, it usually it holds. Let's say it like that.
Because in general, direct sum y and y is their Cartesian product, so it's a little unusual.
Yeah, the usual Cartesian product. It doesn't matter which norm you take on it; they're all equivalent. Okay, you can take the, say, L1 norm, the sum of the two norms. It doesn't matter. Though. Everything here, I'm talking isomorphically in all this lecture. Okay, so let's go to some introduction to the spaces of Rosenthal. So you take a sequence of positive real numbers. I'm talking about p larger than 2. It's easier to describe it for p larger than 2. And I define a space, let's call it XPU. U is the sequence. And it's very simple space. It's just a space of sequences. Real, everything is over the real. And the norm is the maximum between the little LP norm and the weighted little L2 norm. The weights are UI squared. Okay? You can do it also over the complex, but I'll speak over the real. Now, you get, of course, this is a subspace. L2 is a subspace of capital LP, so it's easy to see that also this space is a subspace of capital LP. What Rosenthal proved was that this XPU is isomorphic to a complemented subspace of LP, P larger than 2. And moreover, the isomorphism constant and the complementation constant, the norm of the projection, is in
On your screen, your screen didn't change. Yeah.
What?
Your screen didn't go the next slide
okay,
for whatever reason.
Probably need to stop sharing and share again.
Oh, that happens. Okay. Yeah.
Okay.
So in this case, let's take the questions at the end of the talk. Maybe the interruption is, yeah.
Okay.
Yeah.
So, Rosenthal proves that the spaces are isomorphic to complement. At that time, it was not known. This was at the beginning of the 70s. And there was a big problem then of constructing, of finding the characterization of the complemented subspaces of LP, or finding examples of things like that. And it turns out, this turns out to be a new example. So it proves the following. So of course, sometimes, just 1 minute. Sorry. So of course, if the UJs are going very fast to 0, then if you get only the LP part, and you get little LP. If the UJs are bounded away from 0, you get L2. It's easy to get LP plus L2, but there are situations in which you get a new thing. There are situations in which you get a new thing. For instance, if the limit is 0 and turns up you have some divergent series with right powers, then you get a new space which is different from little p, little l2, little k plus little l2. And so this way, Rosenthal built a new complemented subspace, not one of the classical ones. Now, I don't really know, I never talked with him about it, but I guess that at the time, one would guess that if you take different weights used, you will get different spaces, and maybe you can build infinitely many. And I guess it was it is kind of a disappointment for him. And this is actually not the case. So this is just a repetition. This is just a repetition of the definition. So however, for different use, however, you can get only these 4 spaces: little LP, little L2, little LP plus little L2, and this one new space. Okay. So all these XPU spaces, under the conditions that they are not little LP, little L2, or the sum of them, are mutually isomorphic actually. Okay, actually also with a constant independent of the weights, depending only on P. So I guess that this was a disappointment for Haskell at the time. But anyhow, we denote by XP any of these spaces. Again, I'm interested only in the isomorphic characters of the spaces. Now we need many more properties of these spaces, but right now this is all I need. So all I need is these spaces. I still want to fix weights, so I call it still XPU, and I think of it as a subspace of little LP plus little L2 in the L infinity norm. Yeah, this is a maximum. This is a maximum. Okay. Now, so let me denote by EJ the unit vector basis of little LP, and by FJ the unit vector basis of little L2, and take 2 sequences of weights Vj and Wj tending to 0, and such as the sum of these powers is infinity, so that you really get this new space XP. And also one more condition, I put delta J to be Wj over Vj and assume that it goes to 0. So Wj are much smaller than Vj. And what else? Yeah, I want to set up the basis for this XP. So I call Gj with Gjv will be Ej plus Vj Fj. Remember, Vj is a weight, Ej is a LP basis, Vj Fj is L2 basis, Vj is the weight. So this is a sequence in LP plus L2, and Gj is similar, Gjw similarly with a Wj. So when you do that, then clearly the Gjv is a unit vector basis of XPV, and the Gjw is a unit vector basis of XPW. There's nothing much in what I'm saying, I just need a notation. So I need a notation of this basis, of natural basis of XPV and XPW. Or if you want, these are two bases of this XP. Yeah, okay, this is just a repetition of the definition. And I also want to look at the diagonal operator, delta going from XPW to XPV, which sends GJW to delta J times DJV. So in other words, you can think about it like that. Delta is a restriction to XP of the operator, which I call K, from LP plus L2 to LP plus L2, which multiplies the LP basis by delta J and does not change the L2 basis. Remember, in the definition we had is definition of XPW, where WJ FJ, and in the definition of XPV we had VJ FJ, and now when I multiply by W, I make the weights the same. So it looks like a mistake, but it's not a mistake. It keeps the L2 basis, and it's kind of a diagonal, compact diagonal operator on the LP part. So from this, it's very easy to see that the delta is the norm of delta. Delta is just a restriction of K to XPW. So delta is norm smaller equals than K, and the norm is just the maximum of the delta J's. And the one comes from here. So of course, I'm going to assume that the delta J's are smaller equals than 1, so the norm is 1. The norm of delta is 1. And also, I don't remember if I wrote this. Oh yeah, it's written here. I just repeated this, but I want to say something else. Also, when you go far away in the basis, then you annihilate the little LP part because delta J is going to 0, and the whole weight is on the L2 part. So for instance, you get that for all M, there is an N, such that if you take any M-dimensional subspace E of the tail, it satisfies that this operator factors through a Hilbert space. This is with a bounded norm. Okay, so delta restricted to E, the gamma 2 norm of delta restricted to E is smaller equals than 2. The gamma 2 norm is just a factorization through a Hilbert space. This will be important for me. So for any finite dimension, any fixed dimensional subspace, if you go far away in the basis, any z-dimensional subspace factors nicely through it. Okay. Now I need I'll actually work in the dual situation. Unfortunately, I need to do that. So I'll denote by HJW the dual basis to GJW, and by HJV the dual basis to GJV. And now there were all kinds of properties that were proved by Rosenthal on this. These are now subspaces. The span of the HJW is a subspace of LP prime. P prime is between 1 and 2. And these are nice spaces. I mean, they have all kinds of nice properties. They are, for some reason, they are kind of large spaces. So for instance, it was proved by Rosenthal that the spans contain copies of little r for all r, which is between Q is P prime for me, between the dual P and P, okay? So they contain all the little r's. Now, we need something more than that. And this is a major part of our proof, which I'll not really prove here, but I'll just state. So a major part of our proof is that not only that is the case, but if you take any sequence Ri tending to 2, Ri between Q and 2 tending to 2, and any Ni's tending to infinity, I'm sorry, not just Ni tend to infinity, but Ni to this power. This is a distance of little Lri of dimension Ni from little L2 of dimension Ni. So this distance I want to go to infinity. Now this is the distance between this, I want it to go to infinity. So for any such Ri and Ni, you can find sequences Vj and Wj with a ratio tending to 0, such that, and this is the most important part here, such that if you look at this diagonal, the adjoint of this diagonal operator that I defined before, so this is between the h's now is going, it's a diagonal operator between the h's, it isomorphically uniformly preserves these copies of Lri Ni. So that there are Lri Ni in these spaces was proved by Rosenthal. But I want it to be the same Lri Ni in these two XP V and XPW, the dual space. Okay? And there are more things that this thing preserves. I don't need it, but just remark. For instance, it preserves the modular space L of with exponents Ri. Okay. Now let me tell you what kind of ideas we build once you have this. So the ideas that we build are so you have now, instead of one sequence of weights, you have always two sequences of weights. I'm going to look at this operator. I called it this operator delta star WV. Yeah, this is the dual to this delta. And I look at all operators which factor for this thing. Okay, this is the kind of ideas that I'll build. Later on, there will be something a little bit more involved, but let's start with that. So this is the idea of all operators factoring through this thing. And we do it for different sequences, W and V, different couple of sequences. And moreover, what we really do is we build a continuum of different sequences like that, such that all of these are different. This already will produce a continuum of different ideas. This is not enough for us. We want totally continuum. I didn't say why they are different or anything like that. I don't think that you have to understand this right now. But how do we get to the continuum? We look at okay. If you have a subset of take a subset of this continuum, subset of the continuum. Okay. One can then look at the ideal generated by this operator. So I'm talking now about, I want to use a second way of constructing ideals that I mentioned at the beginning. I look at the set of operators related to this subset of C, okay? And so what we show is that with the right choice of this class, of this continuum of a couple of sequences, if A and B are two subsets of this continuum which are different, then the two closed ideas generated by A and B are different. This is really what we prove. So for every subset of C, we get an ideal, and for different subsets, we get different ideas. So altogether, we get this is a very rough sketch of what we are going to do. Okay, and so that's why you continue, you build that many ideals. Yeah, this is a number of subsets of the continuum. Okay, so how do we actually do it? So we use the following property of properties of this operator. And this is the following. Well, so in a minute I want to state it in a more general form. So I'm stating it already here in the general form, but I'll say what we use it for. So you have a Banach space X with a one unconditional basis. In our case, it is just X star PV. Okay, for sequence V. And you have a one unconditional basis EI, which in our case is just this HIV. Now this is a dual basis to GIV. And you have an operator, a norm one operator, which will be this operator. Okay, so actually you have G and W. But the operator is going from X to X because you remember it's going from the dual of XPW to the dual of XPV, but these are the same, these two spaces are isomorphic by Rosen. So you can look at it as an operator going from X to X. And well, it will not be exactly norm one, but let's say that that it is norm one. This is not the main issue. It has two properties. Okay, so this operator T has two properties, which are the following. This is the most important part. The first property is, I said it before, that okay, for every M, there is a finite dimensional subspace E of X, with such that D of E is a distance from little L2, such a large distance from little L2, and on which T is a good isomorphism. T is of norm 1, and of the inverse is of norm 2. Okay? So this follows from the fact that I said at the beginning, that if you look at the tail of this was stated for P larger than 2, but it dualizes, that if you look at no, I'm sorry. This follows from the last thing that I said, that there are LRI, NI, on which T acts like an isomorphism. And this RI and NI are chosen so that the distance to a Hilbert space is large. Okay? When you have this thing, and T acts like an isomorphism. These E's are this L, RI, NI. This is the first property. The second property is easier, and this is something I stated a long time ago, that for every M, there is an N such that every M-dimensional subspace of the tail going from N and on satisfies that the gamma 2 norm of T respected to E is smaller or equal than 2. This is something I stated in the dual situation for P larger than 2, but it dualizes easily. Okay, so we know these two properties. Right? This I basically told you why. This I didn't tell you why. This is actually the main technical outcome. So we have these two properties. So they look a little bit contradictory. T is an isomorphism on some spaces which are far away from Hilbert spaces, on one hand. On the other hand, if you fix the dimension and you go far enough, then basically T is a Hilbert space, or at least factor for a Hilbert space. So there is some contradictory thing between this thing and this thing. It looks like contradictory, of course, not contradictory.
So if you take, for example, if you take identity on asymptotically Hilbertian space, it will satisfy this, right? If you take identity map on asymptotically Hilbertian space, not L2,
which is not Hilbertian. Yeah.
All right, so it will satisfy this, right?
Of course, yeah.
Yeah, okay.
Gideon.
Okay.
Gideon, one little question. This condition that the norm of Tx is greater than or equal to 1/2 looks somewhat strange. Maybe 1/2 times norm of x. or like that?
You're right. You're right. Of course.
Yeah, okay.
You're right. Thank you. Okay. Okay. And so what we proved is now in the side we proved something more general. We proved the following proposition. So forget now about everything. I use only these two properties. And I already finished my 50 minutes, but I guess I can go on, right? Is that okay?
Yeah, we started a couple of minutes late. Go ahead, finish it.
Okay. Okay. So here is the main proposition. You have a space, I didn't restate it, but X is a Banach space with a one unconditional basis, EI, and T is an operator from X to X, satisfying these two properties, A and B. Then you can find a blocking. So I prefer to write it like that. You can find two increasing interlacing sequences, P and Q, with the following properties. And if you look at the following blocking, so you look, GK is a span of EI and PQ and PQ and A, PK and UK. So these are successive blocks of the basis. You can find things like that, such that the following holds. So first of all, I denote by C a continuum of subsequences of the natural numbers, each two for which has finite intersection. We all know that such thing exists. And for each alpha in C, I denote by P alpha the canonical projection from X onto the span of the GKs where K is in alpha. Okay? So for each such subsequence of the integers out of this continuum. Okay. And so this denotes the natural basis projection, and T alpha is just this thing, P alpha, T times P alpha. Okay. This is a set of, this is a continuum of operators, which are all kind of simple restrictions of this one T. And the main thing is the following. So if you take finitely many elements of C, so finitely many subsequences of the integers, possibly with repetitions, and you take another sequence which is not in out of this collection, but which is not in one of the alpha 1 up to alpha S, and you take operators A1 up to S and B1 up to BS, and you look at, remember how we suggested how to build the ideal in the beginning. You look at such thing, then its distance from T alpha is larger than 1/4. Okay? If you take alpha, which is not one of the alpha 1 up to alpha S, no matter what is A1 up to AS and B1 up to BS, and what is N, and what is S, I'm sorry, this distance is large. Okay? This is the main proposition. Once you have that, it would mean that T alpha is not in the ideal generated by the T alpha. Okay, so if maybe I'll write it. I think I have it in the next slide. So a corollary of that is that if you have such an operator, then L of X in any space in the one unconditional basis, then L of X contains two to the continuum different closed idea. Because you take two different subsets of this continuum, then for any finitely many elements in one of these sets, there is an alpha in the other set, which is not one of these finitely many, and you get that this T alpha is far away from it. So the ideal generated by the subset, the first subset is far away from the ideal generated by the other subset. Okay, I hope it's clear. It's a little bit confusing, but this is the case. Let me just finish with one. I intend to, let me finish with one more thing. From this, you immediately get one simple example of space which has 2 to the continuum ideals, and this is this space. Maybe I will not say anymore about that. This is some, I didn't write it, but it's the L2 sum of LRI, where RI is a sequence spelling to 2. It's very easy to see that this space with LRI, NI is satisfying these 2 conditions. But of course, this space, this is L2 sum. But of course, this space is not does not embed in LP for any P actually. So it's not good as an example. This is why we need this complicated construction on Rosenthal spaces. I actually had planned to give also outline of the proof of the proposition, which is not hard. The proposition is not hard, but I think my time is over by a lot, so I stop it.
Okay, thank you so much, Gideon. That was a wonderful talk. We can take questions now.
Could you say a word about the proof of that main proposition?
I can say more, but it takes some time. Can I say just a word? I don't know. I think it's better if you just look at the paper. It's really short and quite simple.
I have a question. Does it also prove that the operators from LP to LQ, or for some P or some Q, have this many operator ideals? Because you said also you have the same for small ideals, right?
But what do you mean from LP to LQ? It's not the same space, so you cannot speak about ideal.
Well, let's say from LP. So can you? No, I mean the ideals on LP plus LQ, if you want, which is the same as LP to LQ, right? Does it also follow that there are?
For LP plus LQ, of course it gets, because it contains the operators from LP to LP as
essentially the operators.
Projection on them.
Yeah. So this also has to do the
projection onto LP, of course.
Okay.
Any space which contains LP as a complemented subspace will have this problem.
No, but I mean little LP and little LQ.
Oh, little.
I mean little LP and little LQ. So.
No, nothing.
Doesn't, yeah.
I don't know anything about it. No. This is, it's important here, the capital LP. I'm using this XP space as an infinite XP spaces, not like what you use.
Right, you use it as a finite thing for managing little LP and little LQ, right?
Yeah, I really need the infinite.
You need the infinite ones, yeah.
XP space.
Yeah.
But can't you also construct a diagonal operator like the one you did on little LP plus LQ, like sorry, you can't fix LR. So you can't fix everything. You cannot fix that. You can actually fix. No, they're not complementary.
I don't know. Maybe you can.
Yeah, they're not complementary. You cannot fix it. Yeah.
I don't know. Also, two is playing here. I mean, the first thing that you push everything towards 2 plays a role in our proof. One can probably generalize it, but we didn't really try. But it doesn't make much sense. But maybe one can probably do more things with this method. So read the paper. It's a short paper.
Yeah. We got the assignment for the weekend. Okay. Any other questions?
Is there a chance to extend it to reflexive Orlich spaces L5, which are of course not isomorphic to L2, but which could be very close to L2, so you cannot just reduce to the case of capital LP? For your LF1 result with Bourgain and Rosenthal, this can be done as
yeah,
you
I know. By the way, I don't know how to do it. By the way, let me say something. I should have said it before. I mean, it look with always when we thought about large ideals, we thought about building complemented subspaces, but there are only continuum of complemented subspaces, at most continuum of complemented subspaces of LP, and so some, at least some of these ideals are not. So there are more ideals than there are complemented subspaces. This is what I want to say.
Okay.
And by the way, we don't know if there are a continuum of complemented subspaces of LP. We know aleph 1.
Of course, of course. A very fascinating question, by the way. But
yeah, of course. Yeah. So I don't know. I actually tried a little bit to play with it, to try to build new complemented subspaces, but I couldn't.
Well, there is this question which is relevant to mathematical logic, which is called the topological vote conjecture. Whether if you take the action of a Polish group on a Polish space, whether you can have exactly Aleph1 classes, which to the best of my knowledge is still open. But
what? Aleph1 what? I didn't understand.
If you take the action of a Polish group on a Polish space,
yeah.
Whether you can have exactly Aleph1 classes without, of course, continuum hypothesis. And this is called the topological vote conjecture. I mean, Aleko Kekris and such people are experts on this business. But the point is that I thought for a while it was related with a complemented subspace problem for capital LP. But the point is that the isomorphism group of LP is not a Polish group unless P is equal to 2. So the two things happen to be unrelated. Okay, I don't want to spend too much time on this. In any case, it may be nice, or maybe it could be a project for a PhD student to extend your recent work on ideas of LP to reflexive knowledge spaces. I mean, it can be hard, I don't know. Sorry for being so long.
Okay, thank you. Any others? Okay, if not, thank you so much, Gideon, for the talk. So I'm going to stop recording now, and we can